Okay. Good evening. Welcome to October's meeting of the Calumet Nature Exchange. Please advise if a teacher wishes to earn professional development credit. I am recording this evening's session and it will be available on Ollie's website within a week. The agenda calls for self-introductions followed by tonight's speaker, Cameron Nealy. He is a graduate student with the Paleoclimate and Sedimentology Laboratory at IUPUI, and a question and answer session follows his talk. Finally, we need to discuss potential speakers for the remainder of the year. So let's get started with self-introductions. I am Michael Bowes, Executive Director of the Association for the Wolf Lake Initiative.
Oh, do you want all this? Yeah. Mike Galbraith. I'm a board member, just came on this January. Longtime education person and retired. And I'm learning quite a bit through this organization.
Jane Healy.
I'm here, sorry. Just came from another meeting, so I'm joining now. Hello, all.
All right, nice to see you. And Blake is not with us at this moment. But anyway, I've given the introductions, and here's Cameron.
All right, shall I begin?
Yes.
All right, let me share my screen here. Let's see. Okay. Can everyone see this all right?
Yes.
Yes, that's nice.
Perfect. Awesome. Just got to get all the Zoom panels out of my way here, and then I'll start. Okay. Well, come on. Now, my computer's trying to update everything, of course. Thank you all for having me. Thank you, Michael, for the invitation. As you'll see later in the presentation, I and my advisor, Broxton Bird, we were invited out to George Lake a few months ago now at this point to collect a sediment core. And so I was at the Big Marsh event last weekend and got to meet quite a few people who are very knowledgeable about the area. I don't know much about the region in all honesty, and just from the sediment core that we collected have not learned much either. So to make this presentation still somewhat relevant, but stay within my area of expertise, I'm going to talk about some of the other research that we're doing that holds some relevance to the region and how we can sort of extrapolate from those physical records to understand what the climate within the Calumet region would have been in the past, and then hopefully use those interpretations to aid any future interpretation of lake sediment that we might collect. So I'll just begin with introducing myself. I know Michael already sort of did that, but I'm a master's student at University-Purdue University, Indianapolis. I'm finishing up my degree, hopefully within the next year. I'll be graduating in the spring. My undergraduate degree was actually in anthropology. So I entered with intention to study primate behavior of all things. But in my anthropological studies, I got sort of distracted by archaeology along the way. And I was presented with an opportunity to do basically a year-long research internship in the lab that I'm with now. And I stuck around for so long that my advisor now just asked me if I wanted to get a master's degree. So that's what I'm doing now.
That's so cool.
Sorry, what was that?
I think that's so cool. I love how the pathways that people take to get where they end up.
Oh yeah, it's
really cool.
A winding path, and it continues to be. So who knows where I'll go next. But anyway, no, it's a lot of fun, and you will see that because I'm actually going to share quite a few photos of the coring process. So there's one. You get quite muddy, as you can see. All right. So as I sort of preface, the focus of this talk will be paleoclimate, and by that what we mean is paleo being old, and climate is just basically the long-term average of weather conditions. So where we experience weather in sort of a day-to-day format, climate is the mean state variability of those weather and patterns through time. So the lab that I'm working with, the Paleoclimate and Sedimentology Laboratory, specifically focuses on hydroclimate. So that is where climate meets the hydrosphere and the interplay between those two things. So how climate affects water resources and the hydrosphere. So that could be anything from patterns and trends in precipitation, both amount and seasonality. We could look at the relative balance of floods and drought conditions, how snowpack might change through time. Effective moisture is another thing that we're really interested in. That's the balance between precipitation and evaporation. And the reason that we're interested in looking at paleoclimate specifically, because the question might arise, like, why do we care about past climate? Aren't we really just concerned with what's happening now or what's happening in the future? And the answer is yes, that's what we really are concerned with. But climatic patterns have oscillations and variability that operates on centennial and millennial timescales. So pretty long timescales that we can't directly measure with the instrumental records. So if you look at the temperature graph here on the right, this is only the last 2,000 years. So not that much time in the whole scheme of things, at least in the scope of geologic time. But
no more treaties.
Sorry, I got muted there.
Absolutely.
Hey guys, can we mute ourselves so that the only person talking is Cameron?
Okay, I think I'm unmuted. I was just saying though that looking at this temperature graph, the reason that paleoclimate specifically is important is because the dark black line here, that's what we can measure within the instrumental record. Those are direct measurements. It's high resolution, quantifiable. But to understand anything beyond that, beyond 150 or 200 years, we need to use physical paleoclimate archives so that we can understand how climate was, and also so that how we understand how climate will be. So as I just mentioned, we need to use what are called physical archives within the geologic record. And there are many archives that can be used, but the lab that I work with and the research that we do utilizes lake sediment. And there are a few reasons for that. So lake sediment is a great physical archive because it continuously accumulates material. So once a lake forms, sediment is transported to the lake and also formed within the lake from organic material as well. And it does so continuously through time. On top of that, it's pretty high resolution. And the law of superposition basically defines that things that settle out first from the earliest point of formation, those will be at the bottom. And then the newest material will be at the top. So what's great about that is that since it's continuously accumulating and there's a natural order to things, you can then date the cores. So we will send out radiocarbon samples from within a sediment core to get a basal date to understand how old the whole record is. And then we'll get as many points along a core as well so that we can create a really nice age depth relationship. And so this figure here, this sort of diagram, if you will, to the right shows many of the things that contribute to a lake accumulating its sediment. And then once you collect that physical archive at the bottom and take that sediment core, you have all these different proxies. So these, ABC over here in this archive panel are representing any sort of analysis or measurement that you could make on a sediment core, and there are dozens of them. And each one of those is a proxy. It's a direct measurement of something within the sediment that represents a process in the real world, but in past time. So then to the left there is basically a depth relationship with those proxies as a function of time. So every depth step, 5 centimeters down, 100 centimeters down, whatever it is, has an associated point in time with it as well. And another great thing about lakes is that they capture signals and processes on various, not only temporal scales, but spatial scales as well. So lake sediment will tell you things about the local watershed environment. It'll tell you things about regional changes in hydroclimate. Say changes in lake level might be an indicator of increase or decrease in evaporation or precipitation. And then it can also tell you about synoptic or broad continental, even global scale changes in atmospheric circulation patterns. And then also we can record past human climate interactions. And then what I think is particularly of interest probably to this group is the transition into the modern, or as we might describe as the Anthropocene. So in lake sediment records, there's often a marked transition from what we might call loosely the natural past and then into the modified modern period. So again, here's just another schematic showing the different processes that contribute to sediment accumulation. And then if you take a core from that sediment at the bottom, you might wind up with something that looks like this. And in this case, this is a really nice varved sediment example where each one of these light dark color bands would represent basically a year of sediment accumulation. And here is a representation of many different physical archives that we could use to answer questions of paleoclimate. But what this shows to me is that lake sediments are really, really uniquely suited to answer questions on a variety of timescales. So you often find lake records that are very long, but also high resolution. So you can't really get in all physical archives much better than sort of subannual resolution. But of all of those physical archives, lakes also can do pretty high resolution work, but also on pretty long time scales. So that's why we use lake sediments. And also they're quite abundant in the whole scheme of things. You're not going to be able to create a tree ring record from every region in the US, but there are lakes in many places. And once again, here's just showing that lakes are very much suited to answering questions on this time scale. So this is the Holocene epoch, which is the epoch following the last glacial period. So coming out of the Pleistocene, about 12,000 years ago during the last glacial period, we entered the Holocene epoch, and we have lake records even here from Indiana that spans that whole period and tell us about climate of the past, and then also record that transition into the modern industrial present and Anthropocene.
It's up to you.
So anyway, I'm gonna talk now about the process of core collection before talking about the core collection that we did at George Lake itself. We'll talk about some of the issues from George Lake and honestly what we didn't find, and then I hope to use a couple of lake records that I do know about to extrapolate and paint a picture of climate in the region as a whole. So this is the method that we use to collect sediment cores. This diagram here on the left, which I apologize is very low resolution. This is a diagram of a Livingston piston core. So essentially what it is it's an aluminum metal tube with a piston at the end of it. So you'll see that piston here.
I'm giving you my opinion. Ask the Lord. Just ask the Lord.
Sorry. So this is a cutaway. So the aluminum tube here, sorry, just a second. Whoopsie. Gotta go back. All right. Aluminum tube, piston at the bottom, and there's a cable attached to that piston that then exits out the top. So you'll see on the image here to the right, it's sort of a bad picture because it's laying on its side. We're actually, in this case, extruding or pushing the sediment we just collected out the end. But there's that aluminum barrel. There would be a piston there in the end attached to a cable, and then we'll lock that cable off on this aluminum tower that you see here. So in this step-by-step description, you'll see that the core with no sediment in it is being pushed down to the point that you want to start collecting sediment. So in this case, they're collecting sediment at what's called the sediment water interface. You have the piston at the end of the barrel. They'll push the core down to that point. Once you're at the point that you want to start collecting sediment, you will take that cable that runs all the way up to the top and lock it off so that piston doesn't move at all. It's going to stay in place. And then once that piston's locked in place, you basically keep pushing, and then you slide the core barrel over the piston into the sediment. And because that piston's there at the top and it has the rubber gaskets, it basically acts like you have your thumb over the top of a straw if you were to put that in some water. And so I'm just seeing the chat. So then you pull up the sediment, but a lot of people probably don't have it in their minds that when you collect a long sediment core, I'll show an example of one that's like 8.5 meters long. You're not doing it all at once. It's coming up, in our case, 1 meter at a time. So Jane asked how you determine what level to start at. And that's sort of a complicated process. I mean, for the most part, you want to start collecting at the top, right? And to do that, you just use a depth finder of any kind. You can just physically measure with like a weighted meter tape or something. We'll find the bottom of the lake and then do some math to determine exactly what point you want to start at. And then we just keep collecting meter by meter until we can't go any further or we hit the bottom of the record. But the other thing to consider is that you're doing this drive by drive. So each one of these individual pieces of sediment is called a drive. You collect a core, which would be this whole thing up at the top would be considered basically a sediment core. But it's made up of a bunch of pieces. So this from the top all the way down to the bottom where there's sand here, over here on the right, that is about 8.5 meters. This is from a lake we cored this summer near St. Louis. And since you're doing it meter by meter and you can be off a little bit with your math, you actually wind up losing a little bit of sediment between those gaps. And sometimes a little sediment will just fall at the bottom. So to make sure that we actually capture continuously all the sediment, we'll do another set of drives, basically a second core off by some offset. In this case, we offset by 50 centimeters so that the middle portion of one drive will be the overlapping portion of the transition between two ends of the other, if that makes sense. So here, this drive 5, actually overlaps the gap right here. So
Cameron, can I ask a quick question?
yeah,
With all of the slag that has been dumped into Wolf Lake, doesn't that contaminate your attempts to get, true data from the sediment or no?
If we were to core Wolf Lake, and I understand that it's been heavily modified and dredged, which is why we didn't make an attempt to.
Okay.
But if we just pretend that there is nice undisturbed sediment from the beginning of the record where it started, collecting sediment, and then on top of that, there's a bunch of slag that's been deposited. If we could push through that, which it probably would be hard, but pretend that we could collect it, it likely wouldn't affect that early sediment, but it would be something that we'd see geochemically and would be interesting to sort of understand what that looks like. It is possible that I guess some of it could seep into the sediments that it's sitting on top of, but I would think that the rest of the record would be untouched. But again,
Yeah, thanks.
we didn't core Wolf Lake. I think that was the original plan, but we realized that it's been heavily dredged.
Yeah, and on top of that, that slag is like concrete. I mean, it's really, really, really tough, really hard. I can't imagine you'd be able to push a pipe down it unless you were like sledgehammering, and it wouldn't have disturb your results,
Yeah, so there are different coring systems. This piston core here is definitely not designed to go through hard materials. It's not even designed to go through sand, really. Sometimes we collect a fair bit of sand, just sort of on accident. In fact, this record here, this is from, I have slides at the end of the presentation that I can get to, but I'm worried I'm going to go long already. So I'm happy to talk more about that because that's a really cool record that we're working on right now, and has some like pre-Columbian Native American implications as well. But this is from an old cutoff oxbow lake. So it would have been a paleo channel of the Mississippi, and then the Mississippi meanders and it cut off this lake, and then it started to fill with sediment. So it's hard to see here, but this line down here where it's all sand and then turns to sediment, that transition is where it became a lake. So all that sand there is actually fluvial sediment from the old Mississippi River, probably about 2,500 to 3,500 years ago. And then once the lake got cut off and became a lake and no longer was a river, it started to accumulate these much finer grain lake sediments.
That's so cool.
Yeah, no, it's really cool, especially when you get that sand transition at the bottom, because for sure that you've got the whole record. But every lake is different, right? So this would be sort of a floodplain lake, but there are many other kinds of lakes. In fact, I'll talk about some of those today as well. So here's just another picture of this is the full rig when we've got everything set up. That's the tower there in the middle is what we call it. Those rods there attached to the top of the core that I was showing you pictures of so that we can continue to go down. So I saw there was a question about where you start. We do start collecting at the top and then we just keep going down until we, again, can't push any further, like the sediment gets too tough or we hit the bottom of the record. So this tower here has a motorized winch on it. That's from basically, what would it be called? Like an ATV winch, and it's on a pulley system. So this carriage, hard to imagine, but it's basically just a clamp. So you'll push those rods into the carriage, clamp it, and then this winch and pulley system will push the core down into the sediment, and then it can pull it back up as well. Checking the chat again. I will get to that, Blake, if I can. I see your question there, but I'm not sure I'll be able to answer that. But anyway, so this is the haul from Horseshoe Lake that we cored this summer, just showing you that each one of these 1 meter sections comprises what I had showed you a few slides ago. That makes up, a whole core. And this is actually an assemblage of cores from 3 different sites at that lake. And then we also take surface cores. So this is a slightly different coring system. This is more like what we did at George Lake. And I'll show pictures of that as well as a video. But a surface core is a much simpler piece of equipment. It's basically just a polycarbonate tube that has a hat at the top. There's a piston that slides into the tube, and it mechanistically is similar, except you just keep the sediment in the polycarbonate tube for transport. Whereas with the Livingston core, you have to get the sediment out every time. And every once in a while, coring is fun, and you get to jump in the lake and enjoy it. But otherwise, it's pretty hard work. All right, so now I'm going to get to the coring that we did back in August at George Lake. And here's a couple behind the scenes photos. That's Dave McGowan there, who took some really great video and put together a little mini documentary that I'm going to share here in a second. But one of the things to note is just how shallow it is. So this is the deepest part of the lake that he's standing in. And off to the right, closer to the shore, just notice how much sand there is. There's really no sediment that's accumulated at this part of the lake. I wouldn't consider the sand accumulated sediment that's been washed in necessarily. This is more like, in my mind, like the substrate. That's something that we wouldn't be able to core through. So we tried at this location, and you'll see that we really didn't get much. All right. Does anyone know? I'm going to play a video. If I mute myself, do you still hear it?
Not hearing anything.
Can we hear now?
Nope. Sorry.
Ah, dang it.
Is that
I
something
meant
that Michael has? Let's try it again. Let's see. Maybe it'll work now. Is it loaded to YouTube? Is it something that you can pull up from YouTube or Vimeo?
Yeah, let me see. It would be good to show that. So apologies for the break. Let me find it. It's a YouTube video that I downloaded and then linked in the PowerPoint. But I wonder if I could just play it.
Yeah, if you can pull it up on YouTube, you should be able to share it.
Yeah, 1 second. I will see if that works. Man, my computer is really struggling. Oh, I guess it's not published, but I can probably share it here. So 1 sec. Okay, we'll try this one more time. Let me know if the audio works.
I'm not hearing anything. Is the
Dang
volume
it.
on?
It is. I'm hearing it.
Oh, okay. Michael, you gave him control of it. Maybe if you give him the permission to be in charge of the meeting, Michael gives you the authority to be the sort of the leader of the meeting, then he can give it back to Michael when you're done, Cameron. But at least during this video,
Yeah.
then you might be able to share it with everybody. This is the
Yeah.
voice of experience from having to go on teaching for a year and a half under Zoom privileges.
Oh man, I felt like this was going to be an issue. I wish I should have tested this ahead of time. I just don't know how to do that. If it doesn't work, Michael, then it's not a huge deal. It was a nice video, and I know that Dave would probably be happy to share it with anyone who hadn't already seen it.
Dave could
I'd
probably
love to see it if you want to share it my way.
figure
I'm
out.
talking stuff with my students, so.
Yeah, I'm not sure how to give entire control over to him.
That's okay. Yeah, maybe I can just, I assume it's fine with Dave. I'll check with him, but I can probably just share the link. It's not.
Yeah, I mean, if you're willing to drop it in the chat, I mean, we could look at it on our own, but.
Yeah, I think I have to actually physically share it because I don't think it's actually published anywhere. I think he's
okay.
uploaded it privately.
Okay.
Clearly it's hosted on YouTube, obviously, because that's like the player it's in, but I have it through Google Drive. So
Yeah, no, I get you.
anyway, apologies for the technical difficulties, but another time. Okay, we're seeing the presentation, yeah?
Yes.
Okay, well, so there was a little bit of background on George Lake in the video, which would have been nice, but I just want to share the setting here. I think many people are very familiar with the area, and these are actually a couple of photos that were shared last weekend at the Big Marsh event. This is a publication, I forget by who, but it's a paper from 1999, just showing sort of the Lake Michigan shoreline area. There's Wolf Lake, of course, right there on the state boundary, and then Georgia Lake just a little bit to the east of there. And what's sort of interesting to note, and this will come back to be relevant later, I think, is that as you know, over time, as the shoreline of Lake Michigan has sort of progressed northward, as sand is deposited along that north shore, there's this interesting ridge topography with these like radial striations that's formed. And so this is a photo from the 30s before. I mean, there's clearly already development in this area, but before it was just like completely overrun with industry and housing, showing some of that ridge topography. And in those depressions between the ridges, there would be wetlands, little marshes, and lakes that would form. So that's sort of the original morphology, I think, of George Lake, but it's been so heavily modified since that it's not entirely clear exactly where the original boundaries of the lake were. So we did have some trouble identifying where the best place in the lake would be to core, but I think we found the deepest part. This is actually just a screenshot from the video that I was going to show you, and it shows you just how short the core is that we collected. So at the bottom there, where my advisor is putting a black plug in the bottom, you'll see all that sand. So that's the sand that's everywhere in the lake. And where we first walk into the lake, there's nothing above it. It's just sand. When we got to the deepest part, it was clear that we were walking through some actual sediment that had accumulated over time. But when all was said and done, we only got about 14 centimeters worth of sediment, which is almost laughably short. I've never cored a lake with that little sediment, and I don't have a strong sense of exactly why it hasn't been accumulating. Part of it is the length of the record in terms of time. So in talking with some people last weekend, I think we were speculating that George Lake might be as old as 500 years, but maybe not even that old. And right now, we just haven't had the time to do much analysis on it. One of the things we did do was what's called XRF analysis, that's X-ray fluorescence. So it's just a really quick low-hanging fruit type of analysis we can do. It's a gun type instrument, and it basically excites the electrons within a sediment sample, and we're able to look at the geochemical signatures of the sediment core centimeter by centimeter. But of course, there only are 14 centimeters worth of sediment, so there's not a lot to look at. I highlighted these three because I thought there was something there. The other signatures didn't show much. So for clarity, the x-axis is core depth, with the bottom being on the right. So 14 centimeters down is where we hit that sand. And so the silica here is showing that. It's reflecting that really high sand percentage at the bottom. So clearly that's the bottom of the core. And then there's sulfur and lead, which I highlighted primarily because of their, I would say, relevance with regards to industrial production. But I couldn't say exactly, if I could, pick out a point in time historically, like why we'd see a decline or an increase. Sometimes with a longer lake record, you can actually see the abrupt uptick in lead. You can actually then see the decline in lead as legislation, Clean Air Act, whatever else actually encouraged unleaded gasoline and other things. So you can sometimes track that even post modification. We're usually interested in the older sediments, but within the modern portion of the core, you can sometimes almost like manually place a date in time. But I just don't think there's enough here to know what the baseline was, or if there really are any trends or spikes or whatever. So sort of a bummer. I wish this presentation were much more about the core that we collected and everything we learned. But instead, I'm going to talk about some other lake records that we do have a lot of data for, and they're not entirely irrelevant to the Calumet region. So before I get into those lakes, and I'll check the time because I tend to talk a lot, I want to highlight a couple of periods within the Holocene that we are interested in investigating. So that would be the Medieval Climate Anomaly, or MCA, and the Little Ice Age, otherwise known as the LIA. So the Medieval Climate Anomaly was a warm period about 1,000 years ago. And so if you look at this figure here, this is again sort of generalized temperature trends over the Holocene period. And the last two significant blips are the medieval, it's written warm period here, but we call it the climate anomaly. So medieval climate anomaly here is this uptick in temperature, which was generally globally true. There were some exceptions to the increased warmth, but here in the Midwest, it was warmer. And then the Little Ice Age that followed it was a sort of negative temperature anomaly. And then coming out of the Little Ice Age back into the modern period for about the last 2,000 years, temperatures have been much more similar to that medieval climate anomaly. So the reason that we're interested in highlighting these two periods in time is because we can use those basically as two end members of expression to understand the full range of variability of hydroclimate. And the reason that we don't look much further back in time within the Holocene is that global boundary conditions would have been significantly different. So when we talk about boundary conditions, we're really thinking about orbital parameters like the tilt of our axis, the eccentricity of our orbit around the sun. All those things change on their own oscillations. And you'll see this figure to the right here is showing that with those changes, you actually change the amount of energy that certain latitudes on the Earth receive for certain seasons. So Northern Hemisphere summer, for example, would have received more solar insolation about 10,000 years ago. So even if you go back, say, 4 or 5, our global boundary conditions were actually different enough that trying to understand and interpret climate and changes in atmospheric circulation and the complex interdependencies of a global climate system would be not as relevant as we would want them to be for the questions that we're asking. So the first lake I'm going to talk about is Martin Lake. This is a lake in Northeast Indiana, not all that far from Fort Wayne, and a really sort of significant publication that's come out of our lab. So there's a lot of squiggles here. I am very, very happy to answer any questions. So interrupt me, or we can come back to it at the end. So Martin Lake here is situated in a chain of lakes. You'll see it's down here in the bottom right, and these actually were formed glacially. So I may have mentioned that earlier. I don't remember if I did, but sometimes we core floodplain lakes, like they would have been an old part of a river. These lakes here formed as the glaciers retreated coming out of the last ice age. So that transition from the Pleistocene into our current Holocene epoch As those ice sheets retreated northward, they left behind big chunks of ice that would have sat on the landscape, forming a depression as soil formed around it. And then eventually those depressions, of course, fill with water once the ice all melts, and then you're left with a lake. But what's interesting about these two and important is that they're also situated within a fluvial or a stream system where water moves through here pretty quickly. And the reason that's important is because a lake with very low water residence time, as it's called, is not affected by evaporation. And that's a very rare thing. And the reason that's important is because all water has an isotopic signature. So most oxygen, so of course, water has hydrogen and oxygen, and most oxygen is oxygen 16. There is a fair bit of oxygen, though, that's a little bit heavier. It has the same number of electrons, same number of protons, but it has a couple more neutrons, which makes it a bit heavier. And we can use oxygen 18 to create basically a fancy ratio to actually create a signature for any water sample. And water isotopes change with their source. So, for example, this figure here is showing that cold season precipitation in the modern, as we understand it, this is actually precipitation water that was collected over a span of, I think, over a year in Indianapolis, fits along this trajectory. So cool season precipitation has an isotopic signature that is much lower than the warm season pattern. And you'll see that its source is from the Gulf of Mexico. So moisture coming from the Gulf of Mexico is isotopically higher or less negative. So we can use those isotopic signatures to understand how changes in atmospheric circulation in the past may have occurred. And we can only do that if the water in Martin Lake is not changed or not modified by evaporation. When lakes are affected by evaporation, then there's a variable on top of the changes in the source of precipitation that's really hard to remove, if that makes sense. So more evaporation would actually drive these numbers higher. And so if you have changes in the source of precipitation and naturally changes in rates of evaporation, it's hard to really interpret exactly atmospherically what was happening. But this lake, Martin Lake, is very unique in that it's not affected by evaporation. So if you draw your attention to the black squiggly line here, as well as the x-axis, which is time, remember that warm period, the medieval climate anomaly I was talking about, you'll note that values were quite high isotopically from this period. And basically the takeaway from that is that when conditions were warm during the MCA, a lot of moisture was coming from the Gulf of Mexico, much more like this pattern of atmospheric circulation. Then as we transition into the cooler little ice age period, you'll see those values plummet. They go way, way low, and we receive much more cold season, winter-like precipitation. And we interpret it that way because if you look at the line just below it, this is the percent lithics at Martin Lake. So going back, imagine the sediment core physically. We cut that core into 1 centimeter or sometimes half centimeter slices, and then we analyze each one of those slices. And we're able to dissolve away all the organic material, anything other than terrestrial lithic material. And what that means is lake sediment sometimes comes from outside the lake, sometimes it's produced inside the lake. So we get rid of anything that was produced in the lake, and what we're left with is anything that got washed in. So what's washed in is that terrestrial lithic material. So really high proportions of terrestrial lithics in a core sample would indicate that there's much more runoff or erosion in the watershed that would drive that sediment into the lake. So you can think about this figure here, the percentage of terrestrial lithics within the core through time as being an indicator of watershed erosion. So higher values are going to be more erosion, which in this case would be more precipitation, but specifically rainfall, because you could have more snowfall, but snowfall and snow melt is a really low energy event, and it's not going to mobilize that terrestrial material. So once again, remember, medieval climate anomaly, high values, summer-like precipitation, more watershed erosion. That to us says that there is a marked increase in rainfall during that period. But as we move into the little ice age, where it's much cooler, we see much less summer-like precipitation. So a huge reduction in rainfall. So that's something to keep in our back pocket. Sorry. And we can come back to this. I'm worried I'm going to run out of time, but this has very interesting anthropological implications as well. So then the other lake I'm going to talk about is a little further away, but still relevant, because where Martin Lake was a great indicator of synoptic scale changes in atmospheric circulation and other processes, Pope Lake is a great regional indicator of changes in evaporation and lake level. So Pope Lake, as I said, is in sort of central Wisconsin, not all that far from Lake Michigan, which you can kind of see here. So this is its watershed topography. It's also actually situated in a chain of lakes, much like Martin Lake is. And you'll see here's the lake bathymetry, which is important to note because what it shows is like it's not just steep sided. There is sort of a gradual transition. And the reason that matters is because if you can imagine, a lake level can change, and as that lake level changes, say it gets lower because of this bathymetric profile and the sides of the lake that they kind of slope in at an angle and they don't just go straight down. As the lake level drops, you'll actually bring the shore of the lake closer to the core site that we eventually collected from. So there would have been points in time in the past where the lake level would have been higher than it currently is, potentially, where this actually would have been a wider lake, but also points in the past where the lake level would have been lower and the shores of the lake would have been closer. And the reason that matters is because it takes a lot of energy to move terrestrial material, whether it be lithic material or even plant material, to the middle of the lake. And what really helps it is if you bring the shores of the lake closer. That's a huge help. So when we're interpreting lake levels, one of the things we look at is the ratio between carbon and nitrogen counts. So terrestrial plant material is very high in carbon count because carbon helps provide much more structure within the plant biology. Aquatic plants don't need as much structure. There's just they're aided by the water and the gravity isn't affecting them in the same way. So there actually are relatively fewer carbon atoms within an aquatic plant. So we interpret relative changes in the ratio of carbon and nitrogen through time to be an indicator of the amount of terrestrial versus aquatic plant input. So once again, if we go back to this medieval climate anomaly period about 1,000 years ago, it's highlighted in red to indicate that, again, for this whole region, temperatures are warmer. We see that lake levels are actually high. In other words, the carbon count is pretty low. There's not a lot of terrestrial plant input. There's more aquatic plant input, which drives that ratio down. And we see a striking transition into that cooler little ice age period where lake levels we would interpret to be low because there's much more terrestrial plant input. So piecing that together, we now know that synoptic scale atmospheric circulation is driving more summer type precipitation into the region. We have more summer rainfall. So even though it's warmer and potential evaporation is probably higher, we see high lake levels. And then moving into the little ice age, we actually see low lake levels, despite the fact that temperatures would have been cooler. But it's probably because when temperatures were highest seasonally, even though they may have been relatively lower than the warmer medieval climate anomaly that preceded it, we're just not getting as much summer precipitation during this period, which is why we see low lake levels. And then similarly, we can look at this other data as well. I'm happy to explain it, but I will just highlight the CaCO3 here. That's calcium carbonate, which is a mineral that precipitates within the water column and settles out into the sediment. And much like if you were to take some hard water, put it in a pot and then boil it, you'd be left with all the minerals. You get rid of the water, but you're left with the minerals and it'll cake the side of your pan or whatever it is. So you get those evaporation lines. The same thing happens with a lake. So with more evaporation, you'll actually concentrate more of that mineral. And you'll see that there's much more evaporation during the cooler little ice age period. So, I forgot a couple more. These are also relevant, not any research we did in our lab, but there are a couple of bog records. There's sort of like marshy peatland areas. And once again, same sort of story, just a different proxy for changes in effective moisture in this whole region. So Pope Lake would have been like right here in central Wisconsin. We have, of course, George Lake there at the tip of Lake Michigan, Martin Lake in Northeast Indiana. all of these records together encompass the whole area. So even though we didn't get a record from George Lake, I think we can still make some interpretations about past climate in the region. And again, about 1,000 years ago, during that medieval climate anomaly, we see water table as inferred through an assemblage of these microscopic testate amoeba that are very sensitive to changes in water depth and pH and a variety of other things that I'm not qualified to interpret. But these authors were able to quantify that water table was much higher. So in other words, it was a wetter period during the medieval climate anomaly than it was during the Little Ice Age. And we even see that for the whole bog record in Minnesota, there was actually a hiatus where it completely, the peatland basically dried up and there were no testate amoeba. Check the chat real quick. Oh, yes. Indeed. All right, so I actually am coming to the end here, and then hopefully we have some questions before we run out of time. So I'm going to bring it back to sort of the point of this talk, which is what does all this mean for the Calumet region? Because it is unfortunate that we didn't get much from George Lake. I wish there were more to interpret, because I would happily share that with you. But we can still think about some things, I think. To do sort of an overview, what we've established is that about 1,000 years ago, during that MCA period, it was both warm and wet, which is very similar to our modern conditions. But then moving into that cool Little Ice Age period, things got much drier for the whole region. And I think that's interesting to note, because if George Lake, which we don't know, but if we were to send a basal radiocarbon sample out for analysis, I bet that would come back 500 years or younger. Like, it's not going to be much older than 500 years, meaning that as that shoreline was forming and George Lake would have been born potentially 500 years ago, that would have been in the middle of this cool and dry Little Ice Age period. And if that's the case, I wonder if that helps explain why we're not getting much sediment. It's possible that when the lake formed, it was much more of a dune type environment. Maybe it was occasionally inundated, sometimes a lake. Maybe it was more of just sort of like a semi-permanent peatland or marsh type area. And then it didn't become a lake until much later. And as those bog records indicated, water table would have been low as well in the region, potentially. So there's potential that George Lake, if it even started as a lake, that it dried up once or multiple times in the course of its development, and that's why we just don't have much preserved sediment. And so that's probably the past climate, as we can infer from other records in the Calumet region. But we're also concerned with what the future holds. And from everything that we know, from projections, from instrumental data, and from how we understand our paleoclimate evidence, the future looks both warmer and wetter for the area. So you'll see that this figure down here in the bottom right, this is a publication by Malakpour and Villarini, I think from 2014. And I think this was like a 50-year average of gridded precipitation data, showing on the left that in blue, those are areas with positive trends in the magnitude of precipitation, so rainfall. And then the right is the frequency of rainfall, showing also a much more significant positive trend throughout the Midwest. And if you're to read the most recent IPCC annual report, you'll see some pretty dramatic projections for the amount of precipitation increase that we're expected to receive over the next century, even the next 50 years. So the reason that I bring that up is that George Lake, Wolf Lake, the whole Calumet wetlands area is going to be crucially important, just as sort of a buffering resource. And that's something that I think nobody needs to be told. But in a climatic context, I think it's even more interesting. And then something else to consider from sort of an ecological standpoint is I'm curious if moving into the future, as we expect to have shorter winter seasons, warmer annual temperatures, and potentially less ice cover on these lakes that do freeze over, if perhaps that'll affect certain species. I just learned at that Big Marsh event that these mud puppies are much more active during the winter, and you'll actually see them once the lake is frozen over. If a reduction in that ice season could somehow affect how they cope with future climate. So with that, I think that's really all I have to present. There's much more to talk about, and I will be happy to take any questions and hopefully attempt to answer them.
I threw some stuff up in the chat, but I'm just blown away by the concept that you can find evidence of amoebas in those lake core records. Like,
Yeah.
seriously? I don't think of those as being particularly something that would be likely to leave some sort of trace of itself that was, oh my gosh, there you go.
No, so I don't know much about them, but these particular amoeba, these testate amoeba specifically, they often
Got it.
have
So they've got the little silica shell on the outside. Got it.
exactly. So
Yeah.
it's basically like their skeleton in a way, and because they are effectively glass, they preserve pretty well.
Okay. All right. That
And
makes
you can do
sense.
the same thing. You can do the same thing with diatoms. This is actually something we look for. We don't actually interpret, like I couldn't tell you what the different kinds of diatoms are here, but it is something that we're concerned about in our core samples and that we'll check for. And these can tell you a lot as well.
I'm sure. And I assume you're able to find like pollen and things like that too, even in the wetlands.
Yeah, absolutely. That's again something I don't have a trained eye for. We in our lab we just have a lot of collaborators. So there are people that's their whole job. They're just palynologists. They'll count pollen, all the different species, and create a whole pollen assemblage. Same thing with diatoms, testate amoeba. So we have lake records that we've sent out to be sampled for that, but that's something that happens in another lab.
Oh, that's very cool. I also like clearly floodplain resilience and wetland resilience is going to be critical in the near future in the Midwest based on this in the next 100 years or so.
Absolutely. Yeah.
Cameron, are you seeing some preliminary good long-range planning for how all of our communities are going to deal with this excess of precipitation?
Honestly, I haven't seen a lot of evidence in that regard, but I also haven't looked for it. So I mean, I know it's on someone's mind, and I think I guess there are a couple initiatives that I know of, at least in the Indianapolis area, where they're trying to do infrastructural upgrades. I don't know if that is driven by climate projections at all. I would hope that it does factor into their consideration. One of the things that's happening here is dismantling the combined sewer overflow system. There's just so many impermeable surfaces for runoff has to go somewhere. So upgrading sewer systems, and especially in this case, just an outdated system that actually creates a biological hazard for people, will be important moving forward. Because there's just going to be so much more runoff. It's the combined sewer overflow issue will only be more of an issue.
They're also worried about the
vision.
rain
Oh,
bombs.
pardon.
No, I was just gonna say,
Okay.
they're worried about these rain bomb events where the rain, not only is it precipitation, but more precipitation, but it happens really fast. So
Yep.
it's like you get these like massive dumps of water that happen in like an hour versus something that might have taken days in the past.
Yeah,
You
we're
know,
actually seeing,
I have visions
ahead.
of us becoming like the Netherlands.
Mm.
I was there 2 years ago, and they have all these canals. Of course, they built on what they did landfill basically to create Amsterdam in there. But it's fascinating how the excess water, you have to do something with it, and move it, use it, bring it to the drought areas that I assume are still going to exist in the Southwest, places like that. It's like moving the water that's coming. If we can move oil from Alaska, I mean, the size of the pipeline is as big as the room I'm in. I don't see why we can't take Northern Canadian melting snow, and I don't see why we can't take this excess water and move it around the country where it's needed. So it just makes sense to me.
Interesting point. Yeah.
You do it with oil, you can do it with water. What's the difference?
It'll be a bigger issue too. That's something that I didn't bring up in the course of this presentation because I wanted to keep it focused in this region. But one of the primary motivations for coring a lot of these lakes that we are is that there is a sort of this dipole relationship between the Eastern US and the Western US. I
Yeah.
actually have a whole other presentation pulled up talking about that. We could peek at it if you wanted, but we're suspicious that that'll only become more of an issue. So even in the past, like looking at a paleoclimate perspective, in fact, you can look at it on this figure here at the bottom. There's a record from North Dakota, which sort of just crosses that hinge line, if you will. So in time, we sort of see that if you were to draw a line straight down, basically from the western border of Minnesota, areas generally, again, very generally, that fall west of that tend to be, if it's warm, like anomalously warm for a period of time, it's drier as well. But that's not the trend we see here in, say, the Ohio River Valley or upper Midwest. It's the opposite, where when conditions are warm, like during the MCA, it's also much wetter. So the Western US, Southwest, even Western Plains, right, North Dakota, South Dakota, there's a bit of paleoclimate evidence that suggests that in the past, when it was anomalously warm, it was also a lot drier. There's more forest fires, more drought, lake levels drop, but the complete opposite's true in the Eastern US.
And that's
Right.
due in part because of the moist air coming up from the Gulf, right? As the Gulf
Yeah.
water's warmer, then it holds more precipitation and can carries more moisture and can precipitate out. Okay.
That's definitely a part of it, yeah, and that goes all the way back to if you change, again, your global, not boundary conditions, but radiative forcing, right? If you increase radiative forcing on a global scale, one of the things that changes as well, of course, are ocean temperatures. And the Pacific Ocean in particular, obviously to the west of North America here, is hugely influential because we get a lot of precipitation from our prevailing westerly storm tracks over the continent. And so atmospheric circulation is really set up first and foremost by that Pacific Ocean basin. And if you warm the Pacific Ocean, there's all these sort of internal climate mechanisms that change, and that changes the mean state atmospheric circulation. So this paper here in particular relates to the most relevant climatic pattern that we can measure that affects the Midwest, and that's the Pacific North American pattern, which basically defines the circulation pattern that you're seeing here. So a negative PNA pattern, which doesn't mean anything to anyone at this point, but atmospherically, that can be set up as like a mean state average type circulation. And that's what was happening during the MCA and is happening now during the current warm period, where most of our moisture is being delivered from the Gulf of Mexico. But that sort of atmospheric circulation pattern actually also similarly relates to less moisture being delivered to the Southwest United States. So those two go hand in hand.
Right? Did you have a question?
Excuse me, I have a question. I
Yeah.
just want to find out, what are some key wildlife species that are thriving in or near George Lake?
I think I might be the wrong person to answer that. Unfortunately, I'm not exactly an ecological expert on the area, and if I knew who was, I would direct you that way. But I'm sorry, but I cannot answer that, Blake.
I have another question regarding to climate.
Mhm.
And what's the climatic condition not only at George Lake but also at Lake Calumet and other places around the Calumet?
No, good question. That's sort of the beauty of these sediment archives that we use to investigate paleoclimate is that these changes we're talking about are sort of synoptic in scale. So the exact like local watershed level changes that are happening at this Martin Lake record that I'm showing here probably aren't relevant for the Southwest because very different things would be happening there. But this lake record represents global changes that then affect synoptic scale or continental scale variability in atmospheric circulation. So that's a lot of words basically just to say that this Martin Lake record that we see here actually does describe the atmospheric and on the ground climatic conditions that would have been happening in any of the lakes in the Calumet area. If we look at the Pope Lake record too, where I was emphasizing low lake levels, more evaporation, potentially more drought-like conditions during the Little Ice Age, that would have been happening, I would imagine, at, again, any of the lakes in the Calumet area. So Lake George, Wolf Lake, Calumet, or yeah, any of those. Of course, there's going to be nuances, right? Like the reason that you investigate a lake to the depth that we do is to understand like how to interpret the data. But once we're confident with an interpretation at a lake that's 100 miles away, the same thing is honestly probably happening at that lake as well.
You catch the latest river dryout from the latest river dryout in China, as well
No.
as back home the Mississippi.
No, I had not read about that.
But you know
Good enough.
about the Yangtze. But you know about the Yangtze about the river drought in China, and what's your take on it?
I actually don't know of that. I probably should. You do more reading than I do. You should be given the talk.
Okay, any more questions?
China.
Wow.
Thank you so much for this. This was super interesting.
Yes. Thanks very much. I appreciate that. You spending the time. I'll check up on you in the spring and see what you are going to decide with your life, Cameron.
I'd appreciate that. Hope,
The next couple of years anyway. So
yeah. Hopefully I have it figured out by then.
okay. And I was just I don't know if you know the history of George Lake, but 100 years ago it was about the size of Wolf Lake.
Oh, was it?
Yeah, and in the 1920s, Hammond thought there was an interest in building a steel mill, so they filled it all in,
Yeah.
half of it in, and at least half, and steel mill never came. So so that's what happened to it. So at 100 years ago, it was twice as large or 3 times as large as it is today.
Okay, I'm not sure I had seen that. I know that when we were planning and looking at it, where we should core in the lake, that's something I should have shown here. I just I didn't run across that map, but we were looking at like a historical, basically street map that showed George Lake being sort of this really skinny northeast to southwest sort of lake, like even smaller than it appears today. So I was unaware that it would have been much larger at that point. So when we were trying to basically take a really old map that was just kind of almost drawn in and calibrate the modern basically modern satellite imagery to know exactly where in the lake we should core, because we wanted to be at where the deepest point would have been. And we were thinking that the current lake extent is actually bigger than it would have been back in, I think the map was from like the 20s or something. But it sounds like that maybe would have been just after it had been filled in.
Yeah, it would. And I don't know if it was ever, how deep it was, and if it was just a large wetland as opposed to a lake. Certainly what's remaining is the north part is very shallow. 3 feet probably at the deepest.
Yeah, I do wonder if maybe it was just like an extended wetlands area. Maybe it wasn't even like a permanent lake all the time. But.
In the 1890s or 1880s, Wolf Lake was a wetland, and humans changed it, so it is now a lake, and they filled in other lakes, nearby lakes. So and I've never seen a map of the the larger George Lake. So but I've been told that, and in fact, I have seen a map, and it was surprisingly that it was very much close to the size of Wolf Lake.
Yeah, I'm surprised to hear that as well. I'd be interested to see that. And it also makes me think of, the changes that have happened at Wolf Lake. I'm reflecting on Phil's talk at the Big Marsh event, how he was talking about sort of that ecological succession and that natural trajectory that lakes in the area would take, and how now as like stewards of the lake and of the restoration process, that a conscious, deliberate decision almost has to be made about what direction it goes. Does it continue to revert because it's kind of taken a step back, or do you write it on that path? And I think taking some of this climatic perspective into consideration will be important for making that choice, whether it goes back to being a wetland or it's a lake and then transitions into a more of a, whatever it may be, a more wooded area. I don't know.
Yeah, and we don't know, but anyway, that's a human intervention sometimes deepens lakes and sometimes just fills them in. So as we see here, so that's kind of the history of at least those two lakes. So anyway, Cameron, thanks very much, and for coming up, and we wish you well in your studies.
I appreciate it. It was an honor to be here. Thanks for the invitation. Thanks for the questions, everyone. And
thank you so much.
Appreciate your time.
Thanks a lot, Cameron.
You have a great future, I think. Hang in there. You're doing well.
Appreciate it. Thank you.
Even if your pathways varied and strange, I love that. That's great about
it's
pathways.
been all over the place.
That's the best way.
I agree.
Okay. All right, I'm going to stop the recording right now then.
Bye, everybody. Thank you.